So if I were to say fz is a polynomial, a general polynomial like what we have discussed just now, right, will look something that is like this, to the power of n, where a0 represents the coefficient. Okay, you don't have to copy this because it's the green color thing that I showed you just now. Then the next one will be like, for example, a1, then z to the power of n minus 1, a2, z to the power of n minus 2, all the way until an minus 1, z. Then the term that is independent of z is an. So a1, a0, all the way until an, they are coefficients of the polynomial. And if I were to tell you that w is a root, so if w is a root of fz, if w is a root of fz, I know that fw is equal to 0. Okay, right? But this is still using what we have learned in our secondary school. Then if fw is equal to 0, then a0, w to the power of n, a1, w to the power of n minus 1, all the way until the very last term, which is an, the term that is independent of z, this will be equal to 0. I just simply replace all the z by w. Okay? And the next thing that I'm going to do is, I cannot really explain to you why I'm doing that. I believe that whoever did that, right, probably has gone through 1,000 different ways of changing this before deriving that, hey, this can actually help me to progress. And to progress from here, I'm going to go back to my outline and I'm going to start using all this conjugate stuff that I asked you guys to read last week. So what I'm going to do is, I'm going to take this entire left-hand side, I will conjugate. I'll take this entire right-hand side, I will conjugate. Again, why do I want to do this? I don't know. The first person who did this is probably had tried a few different methods and ended up realizing that, hey, this will actually work. And let me show you how this will work. So if I were to apply this conjugate thing, if I were to apply number 1, this tells me that this whole thing conjugate is going to be equal to a0, w to the power of n conjugate. It is a1, w to the power of n minus 1 conjugate, all the way until an conjugate is equal to 0 conjugate. Let me talk about 0 conjugate. 0 is a real number. Just so that we can see it more, in a broader sense, right? Let's say I have a 3 conjugate. 3 can also be seen as a complex number because 3 I can see it as 3 plus 0i. So what do we do when we have a complex number and we let it go through the conjugate? The imaginary portion will be negated, which means that this will become 3 minus 0i, which actually is still going to become 3, which means that a real number, when you conjugate it, actually is still going to be exactly the same. A real number conjugate will still be the real number. So 0 is like 0 plus 0i. Conjugate, it will become 0 minus 0i, which is actually still 0. So on the right hand side, 0 conjugate will remain as 0. As for this, I'm going to now apply number 2. Number 2 tells me that I can rewrite this as a0 conjugate, then w to the power of n conjugate, then a1 conjugate, then w to the power of n minus 1 conjugate, all the way until the very last term here, which is an conjugate. This is equal to 0. And just in case some of you are starting to think in a wrong way, which is, hey, if he wrote 0 conjugate as 0, why didn't he write an conjugate as an? Why did he just continue to write an conjugate as an conjugate? Thomas, what do you think? Why do you think I continue to write an conjugate as an conjugate? Why don't I just simply write it as an?
It could be
Yes. Okay, this is a very, very good way to approach complex number. Like what I was saying just now, any unknowns that are given to you, please, starting from this topic, you can no longer take it for granted that it is always going to be real numbers. Like what Thomas has just mentioned, right? It is actually possible for, I define this as a polynomial. I didn't say that this polynomial has real coefficient, which means that the coefficients could have been complex number. That is why an conjugate, I continue to write it as an conjugate. And if I were to apply next number 5, number 5 tells me that I can rewrite this as w conjugate to the power of n. Then this will be a1 conjugate. This I can write it as w conjugate to the power of n minus 1 all the way until this I will let it retain as itself, an conjugate. Okay, if I were to apply number 5. And here is where I'm going to introduce a condition. These are just manipulation. It doesn't add to the value of how we're going to solve for polynomial yet. But if this is a real number, if this is a real number, if all the coefficients are real number, all the coefficients are real number, if all the coefficients happen to be real number, then it will behave in the same way as this. That means if ai, where I is 0, 1, 2, 3 all the way until n, if ai are all real numbers, okay, that means I can write a0 as, I can write a0 conjugate as a0. Then it will be this, w conjugate to the power of n, then this will be a1, then w conjugate to the power of n minus 1, all the way until this will also become an. This is equal to 0. Okay, provided that this happen. If this doesn't happen, then this line will not happen. Then this line will just end here. I will not be able to get to another line. But you know, if this happen, I can write it into this way. And if you to now compare this to this, can you see? All the z is being replaced by w conjugate, which means that this entire left-hand side, I can rewrite it as w conjugate is equal to 0. Okay, we are seeing a special result here. The special result is if w is a root, if all the coefficients are real number. If w is a root, if all the coefficients are real number, then automatically w conjugate is also going to be a root of the polynomial fz. Okay? If w is a root, all the coefficients are